Let's imagine that we take this seesaw off the center balance and we put it on two supports that balance it at each end. And that 75 kilogram child, let's imagine, stands on the plank, or the seesaw, 1 meter from the left end. The question is now, what forces do these two supports have to apply on the seesaw to keep it stationary? Again, what's the object that is not rotating? It's the seesaw, so we know, in addition to the fact that the total force acting on the seesaw has to be 0, the total torque acting on the seesaw has to be 0. Let's draw our free body diagram. Let's draw in our forces. What forces are acting on the seesaw? Well, we know that the weight of the child pushing down on the seesaw is going to be acting on it. So we've got a force from the weight of the child pushing down. We already know the weight of the child, mg, 9.8 times 75 kilograms, that's 735 newtons. So we have a force of 735 newtons. Then we have the supports from the forces from the supports at the two ends. I'll call this force, say, F sub L for the left force, while this one, we know the force is pushing up. This one we'll call F sub R for the right force, the force on the right side. Very good. Now, let's take a look at the, now we know, well, let's start with the forces. I guess we can start out with what equations deal with the forces. There are no forces in the x direction. If we were to choose our x and y directions like this, we know there are no forces in the x direction. Let's look at the forces in the y direction. We know the net force in the y direction has to be 0 because it's not accelerating in the y direction. So we know F sub y equals, what forces act in the y direction? Well, F sub L, and is that positive or negative? Positive. F sub R, again, positive. And then the weight of the child is 735 newtons. Is that positive or negative? That's negative. So minus 735 newtons. What's the net force in the y direction? We know F sub y equals MAY. The seesaw is not accelerating. A sub y is 0. We know that has to be 0. So all of this has to be 0. Bring the 735 to the other side, and we know that F sub L plus F sub R must equal 735 newtons. Sorry, let me just mention again, we're assuming that the seesaw is massless, but as soon as we finish with this problem, we'll stick in a mass for the seesaw and see what happens. There we go. We know that the sum of F sub L plus F sub R is 735 newtons. But we don't know what each value is. To figure out that, we need to look at the torques. To determine the torque, what do we have to choose? Remember, we have to choose the location of our origin. We can put our origin anywhere we want. Where might we want to put it? Remember what we found last time, that any force that acts at the origin contributes 0 torque. If we choose our origin at the location of one of our forces, that force will not give us any torque. We have two unknown forces. If we choose our origin at the location of one of those forces, then it will not contribute any torque, and we'll have one fewer unknowns in our torque equation. Let's take advantage of that fact. Why don't we put our origin at this end? And when you do a problem like this, I would always suggest draw in your origin and write down origin so that you remember that's the origin. And whenever you need to calculate a value of R for one of your torques, you'll always remember you've got to measure that R from that point. Very good. Let's figure out what are our torques. Let's do these 1, 2, 3. So the left torque, the left force, what is the torque due to the leftmost force? Hopefully you realize that. That's 0 because R for that force is 0. That was the whole reason why we put the origin there. So torque for the left force is 0. What is the torque for the weight of the child? So I'll say torque W, torque for the weight of the child. Remember, torque, RF sine theta. What is R for the weight of the child? What's the distance from the origin to the point where the weight of the child is being applied? It is 1 meter. What is F for the weight of the child? 735 newtons. Sine. What is the angle for the weight of the child? Well, R, F, what is it? 90 degrees. And is this, remember, what's the last thing we always have to ask ourselves? Is the torque positive or negative? Is this a positive or negative torque? Think about this. Is this force tending to rotate the seesaw clockwise or counterclockwise? Remember about the origin. Is it going clockwise or counterclockwise about the origin? In this case, here's the stick, here's the origin. It's being pushed down this way. What is that? Clockwise. Another way of thinking about this is just continue this around the origin, and that is clockwise. So what is it? Negative. That is a negative torque. Good. Multiply this out, and what do we get? We get negative 735 Newton meters. Newton meters. Very good. What about the torque due to the right side? The torque due to the right-hand support. What is R for the right-hand support? That is, here's the origin, force, 3 meters. Times F, what is the force? It is F sub R. We don't know what it is, but we've got to call it something in order to be able to solve for it. So we'll call it F sub R. F sub R, sine, and what is the angle? I hope you can see it is also 90 degrees. Multiply that, and the last step, is it positive or negative? It is positive. Continue this around the origin, and it is counterclockwise. Or look at how is it pushing the seesaw? Pushing the seesaw around counterclockwise. So that is positive. Multiply this out, and what do we get? We get 3 FR, or 3 meters times FR. What is the total torque? The total torque is the sum of all of the torques, which is 0, plus the torque due to the weight of the child, minus 735 Newton meters, plus the torque on the right side, 3 meters FR, plus 3 meters FR. What's the total torque? The total torque, because the seesaw is not rotating, the total torque must be 0. So this all must be 0. Bring this term over there, divide by 3 meters, we have FR is equal to 735 Newton meters divided by 3 meters, or FR is equal to 245 newtons. There we go. There is the force from the right side. What is the force from the left side? How do we find that? Well, we can take this and put it right into this equation. FL will be 735 minus 245, which leaves us with FL is equal to 490 newtons. Very, very good. To recap, how did we do this? Again, we drew a free body diagram, being very careful to make sure that we drew all of the forces at the point or points where that particular force, each point where that particular force acted. Left force over here, the weight of the child here, right force over here. We looked at the force equation first, in this case, the y forces, to give us a simple relationship between the left-right force and what we knew the total had to be. Then we looked at the torques. we had to define an origin. In order to determine torques, you have to choose an origin. We did that. We determined the torque due to each force. We added them together. We could then solve for one of those forces. Remember, by choosing the origin at the location of one of the unknown forces, we removed that from the torque equation. In other words, the torque due to that force was 0 in that case. That allowed us to solve for F sub r, and then from our force equation in the y direction, we could solve for F sub L. Very, very good. Now, what if the plank had a mass? Let's just imagine the plank has a mass of, let's say, 10 kilograms. Let's imagine our plank has a mass of 10 kilograms. How does that change the problem? Well, we have an additional force. What is that force? It's the weight of the plank. We have to put the weight of the plank into our free body diagram. The problem is where? Where do we put that force? Where we put that force is very important because that's going to affect how much torque that force applies. Let's think about that for a second. Let's come back to our stick here, the meter stick. The stick has a mass, a small mass, but it has a mass, and that mass creates a torque on this stick, or it could create a torque. I'll be a little more careful about that. Now let's think about that. How does the torque due to the weight of the stick tend to rotate this stick? Well, if I hold it over at this end, and I'm going to let go with my left hand, if I hold it at this end, the weight of the stick tends to rotate the stick in a clockwise direction. In other words, it tends to pull it down this way. If I hold the stick at the right end, your right, and I let go of the stick, the torque due to the weight of the stick tends to rotate the stick in a counterclockwise direction. However, if I hold the stick at the very center, we get 0 torque. There is 0 torque. The weight of the stick does not tend to rotate the stick. So the torque must be 0. Well, this gives us a very, very good idea of where that force is acting. If I hold the stick in the middle, the weight of the stick creates 0 torque. What does that tell us? The force must be acting at the location of the origin. In other words, at the location of my finger, the center of the stick. This is an interesting result. The weight of an object acts at every single point of the object. I mean, the part of the stick over here has a weight, and the weight of that acts over here. This part of the stick over here has a small weight and acts over here. This part of the stick has a weight and acts over here. This part of the weight acts over here. This part over here. This part over here. So gravity is pulling the stick down at every single part of that stick. But we can add all of those weights together into a single weight vector. And that weight vector seems to act at the center of the object. And that is true for anything we want to deal with. Whenever we want to take the weight of that object into account in terms of the torque that it's applying on the object, we can always assume that that force acts at the center of the object. In that case, this weight, if the weight is like this, if that weight is acting right here, at the center of the stick, at the origin here, if we put the origin here, the torque is 0. If I hold it over here, in this case, the torque is clockwise, and that would tend to rotate the stick clockwise. If I hold the stick over here, and this is the weight, here, that weight is counterclockwise and tends to rotate the stick in a counterclockwise direction. This is a very, very important point, and we are going to come back to this on numerous occasions. The weight of an object acts at its center. what do we mean by the center of an object? What is the center of this weight? Where do we put the center? Well, if it's a symmetric object, the center is the center where the weight acts is at the center of the object. Well, in this case, there's a hole there, but that's okay. It actually can act at a point where there is no part of the object, as a matter of fact, the center of the object. This is a very, very interesting result. We'll come back to this. We'll define what we mean a little more quantitatively where the center is just at the end of the lecture. So we'll come back to this, but let's just keep in mind the center of an object is, the weight of an object acts at the center of the object. Well, where's the center of the seesaw? Where do we put the weight? What's the weight of the seesaw? Well, if it has a mass of 10 kilograms, the weight would be 10 times 9.8, or 98 newtons. So where does the weight of the seesaw act? It acts at its center. So at the very center of the seesaw, right here, we'll put an additional weight of 98 newtons. How does that affect the rest of these results? Well, let me put those in there and then we'll see. Including the 98 newton weight for the seesaw, we have to put that into our y forces. So we'll have an additional minus 98 newtons in our y equation. Minus because it's pointing down. Which means then that FL plus FR will be 735 plus 98, or 833 newtons. We then have to add in an additional torque. The torque due to the stick, tau sub s, torque due to the weight of the stick. What's R for the weight of the stick? That's going to be half the length of the seesaw, weight of the seesaw, I mean. Half the weight of the seesaw, which is 1.5 meters, times R, times F, which is 98 newtons, sine theta, again 90 degrees, and this is in the clockwise direction, so again it's negative, which gives us a torque of negative 147 newton meters. Putting that into our torque equation, we then have an additional minus 147 newtons, or FR is then going to be adding in that 147. 735 plus 147 is 882, then divided by 3, and we end up with 294. Putting in the 294 to our force equation, 833 minus 294 leaves us with FL is 539 newtons. Very good. However, just notice that our new answers, 294, that's 245 plus 49. And our new answer for the left support, 539, that's 490 plus 49. In other words, these new answers are our old answers, but each one increased by 49 newtons. What does that mean? Well, 49 newtons, that's exactly half the weight of the seesaw. In other words, by adding in a weight of the seesaw, we have increased each force by half that weight. In other words, each force just supports half the weight of the seesaw plus whatever else we also put in there, the weight of the person. So interesting. The net result, the net change, is exactly what we might have guessed right from the beginning, that when something is supported by its two ends, the two ends are just each supporting half the weight of the object. Well, very, very interesting. Let's try another example. For this one, every angle that we had was 90 degrees. Let's try another problem where we've got some different angles in there.